Hi everybody, welcome to Operating Systems 1. I am the teacher for this course, Benjamin Brewster. I am glad to have you along. So let's talk about what we're going to be doing in this course. So operating systems is all about what makes the user be able to interact with the hardware. How can that operating system manage the resources of that computer for the use of the user? So there's always the struggle between trying to teach theory versus tools. Is this a technical degree? Is this a computer science degree? So is it C++? Are we learning Unix? Are we learning Java? Are we going to learn about Windows at all? Well, you're computer science majors, not Unix majors. And that's an important distinction. So after this class is over, you should be able to hold some sort of intelligent conversation about any operating system, since we're going to be studying our model operating system, which is Unix. It's a great model operating system, but it doesn't mean that just because we study it, that's all we do. That's all we're concerned with. So why would we study something like Unix? Well, for the most part, it is extremely simple compared to other operating systems. It's been around for a long time. It's very stable, it's very powerful, it's completely standardized in the sense that it's everywhere. There's different flavors of it, of course, between BSD and Linux and the actual Unix that still exists that's out there. In terms of shipments of devices just in the year 2015, so the Android phones were shipping, 1.3 billion of those things in 2015. So Android is a fork of Linux. Compared to Windows, which is 283 million, iOS, which is a flavor of Unix, specifically its BSD variant, is 276 million. The desktop operating system used by Apple, OS X, is 21 million. Again, that's a BSD variant. And there's a bunch of others, some of which are Linux, which rounds out the rest. So out of all those devices that shipped in 2015, and certainly round numbers here, Unix is running 82% of those. That's enormous. Sometimes we don't think of how pervasive Unix actually is. So understanding why we would teach Unix is there are lots of reasons to it, but again, to recap, it's used everywhere, and it is stable and old and powerful and easy, and it's classic. You're going to love it. So what is that operating system? It is a software program that sits between the applications that we use and the hardware that's there. So if you take a look at our little examples, let me turn on my little laser here. There we go. So if we've got our computer hardware, then that thing is separated from our user programs by the operating system, kind of on a gross overview here. Certainly there are drivers that sit in between the hardware and the operating system, but in general, the operating system is our interface to the hardware itself. So why are these operating systems important? Well, most of the applications that we write, that we use, interact with the operating system in some fashion. And as a programmer, you'll need to know the capabilities of whatever operating system you're using to get the most out of it. And it also will teach us to understand the limitations of the operating system that we're using, because not every operating system is suited for every task. So here's a list of some of the goals for operating systems. Our universal ones are here at the top. Pretty universally, we'll see that they are providing a convenient software interface to that hardware, like we've been talking about, with the goal towards maximizing the utilization of that hardware. Even though we like to see our little CPU tracker telling us that we're only using 2% or 3% of our CPU, what we'd really like to be seeing is that our CPU is perfectly matched to everything that's happening, that all of our software is running as fast as it possibly can, and that nothing is ever waiting. That would be best. That operating system should solve the contention inherent in having lots of processes that want to use the hardware at the same time. So we've solved this by making our hardware more capable in the sense of having multi-core CPUs and being able to multi-program and multi-process all at the same time. And we'll talk about that as we get further into the course. But the operating system will solve the contention between all of these different processes that want access to the hardware. It'll also provide a set of services that are going to provide a benefit to the programmer and to the user so that they don't have to reprogram that and have to reinvent the wheel every time they try to write a new piece of software. Some common goals, which are certainly not universal, would be to provide security. Not all operating systems have as a goal to provide security, or rather, they achieve the security by being so obtuse, so inaccessible, that they don't particularly worry about the security features. So that's certainly one part of it. And there's two parts to security. One is not just that we're keeping the bad guys out, but that we're protecting our software from other buggy software that students like ourselves will be writing in this very course. So security is kind of a two-edged sword there. We want to keep the bad guys out and keep our fellow colleagues from writing software that hurts ours, but at the same time we don't want the security to be so interfering that it prevents us from easily using the system. So a common goal for Unix is going to be that it supports software development very, very well. There are lots of built-in tools that enable us to use Unix, way more so than Windows. The tools for Windows are very available, but they are not built in. And it's nice that Unix has most of the stuff just pre-built for us. And there's a whole bunch of standardized software libraries that are easy to use, easy to access, that have been around for decades, where there's lots of help material online to help us out. Let's look at some definitions really quick. A program is going to be a stored algorithm. It's the plan of execution. It's the recipe sitting in the recipe box. It's something that we can do whenever we want to, but that we're not currently doing. That's what we write. That's a program. A process, on the other hand, is a program that's been loaded into memory and that we're currently executing on. Now, it might be, paused for a moment. It might be blocked because of input-output that's running. We'll talk more about that as we get closer. But the distinction between the two is the process has been pulled off its storage medium and pushed up into RAM for the purposes of being executed. In other words, a thread is a line of execution within a process. So the process might be doing multiple things at once. It might be collecting input and outputting data and handling network connections, and each one of these tasks might be a separate thing that process is doing. When they are given a sense of when they are given independence, when we allow them to actually proceed from step by step in their line of execution independently, we would call those threads. This is in contrast to merely having your program do one thing for a bit and then switch to something else and then do that for a little while. Threads can run concurrently. They can run at the same time. So, looking a little deeper at some of the services that are available, that are commonly available on operating systems, they will all do process and thread management. So they're good at starting new programs, which is what creates processes and threads. They are good at killing them off, and they will help us debug them. We like to see these things. They can also help us to organize our bits into meaningful structures. We'll call them files and directories for creating a hierarchical representation of where individual files are stored. They'll give us a method for reading and writing to those files and a way to communicate with external devices. So flash drives, Blu-ray players that are connected, even network connections might be represented as a file in the operating system. We'll also see inter-process communication being a big part. Inter-process communication means just what it sounds like, how the processes talk to each other. So signals and pipes and sockets and communication that happens on the computer versus communication that happens from computer to others on the LAN or across the internet. These operating systems will provide a method for the processes to communicate with each other, to inform each other on what's going on, to shut things down when they need to be shut down, all kinds of stuff. We'll also see process coordination. So this is the contention management stuff that we talked about, where the CPU is going to have to decide which process gets to run right now based on priority, based on fairness, based on need. To interact with the operating system, the users typically are going to use a GUI, a graphical user interface, or some sort of command line shell. We'll see all those kind of things. programs are going to access the operating system using functions. This will be system calls, which is where the program asks the operating system to do something for it. We'll also see the programs use application programming interfaces, APIs, to access stored libraries worth of functions. And also, we will see programs interact with the operating system via the network. They can ask the operating system to start up a message-based connection from one process to another, and again separated between multiple computers even. And it could also be asked to set up something that is connection based. So think of a established connection that is always in place that allows us to send data back and forth, versus something where it's just messages, where you just blast data across the network and hope it gets there, but you don't actually maintain a connection. I hope that you have fun in this course. There's a lot of semi to challenging subjects that are in here, but I do think it's worthwhile. I think this is one of the seminal courses in our whole program, and I'm honored and humbled to be able to teach it. I do hope you have fun. There is a lot of great material here. Feel free to dig deep, and I will be as involved as I can. We'll see you on the discussion boards via email, and for those of you that I see in person, I'd love to see you there too. Make sure to have fun, and we will see you next time. Thanks!